So in our previous lectures we discussed Ampere's law, and today we are going to discuss few applications of Ampere's law. So here the first one is solenoid. Solenoid consists of a helical winding of wire on a cylinder or usually circular in cross section. There can be hundred or thousand of turns, but turns of closely spaced. Each of which can be regarded as a circular loop. So here for simplicity we showed a solenoid, and it has only few turns, and all turns carry same current, and the total magnetic field at every point is the vector sum caused by the individual turns. Here in this figure the field lines lie in the x, y and xz planes, and we can draw a set of field lines that are uniformly spaced at the center of the solenoid here in the other figure. Uh, exact calculations of the solenoid show that for a long closely wound solenoid, half of the field lines emerge from the ends and half leak out through the windings between the center and the end. So the field lines near the center of the solenoid are approximately parallel. And if they are parallel, it indicates uniform magnetic field. Outside the solenoid, the field lines are spread apart, or here, and the magnetic field is weak. If the solenoid is long in comparison with its cross-sectional diameter and the coils are tightly wound, the internal field near the midpoint of the solenoid length is very nearly uniform over the cross-section and parallel to the x-axis. Parallel to the axis. And the external field near the midpoint is very small. So now we can use Ampere law to find the field at or near the center of such a long solenoid. The solenoid has n turns of wire per unit length and carries a current I. So this is a symmetrical situation where a magnetic field is uniform inside the solenoid and zero field outside. So we can choose a rectangular path, which is a path of our integration, and this rectangle has this rectangle has points A, B, C, D. Side AB has length L, and it is parallel to the axis of the solenoid. Sides BC and CD are taken to be very long, so that side CD is very far from the solenoid. Then the field at CD would be negligible, is small. So by symmetry, the magnetic field along side AB is parallel to this side and is constant. In carrying out the Ampere's law integration, we can start from the side AB and in the same direction as B. So for here AB, for this side AB, B dot L becomes BL. For BC, becomes 0 because B parallel is equal to 0. And the same for side DA. And also along CD, the integral path is 0. So your the entire closed path B dot dl, so this is 0, this term 0, this term 0, so your closed path becomes equal to B dot dl. So the integral B dot dl around the entire closed path reduced to BL. The number of turns in length L is NL. Each of these turns passes once through the rectangle ABCD and carries a current I. I means the current in the windings. So the total current enclosed by the rectangle would be I enclosed, and this becomes N L I. From ampere law, since the integral is positive, I enclosed must be positive. So this integral ampere law is V dot dl is equal to mu naught I, and here becomes B L mu naught N L I. So the Ampere's law gives the magnitude of magnetic field here, and B becomes mu naught and I. Side AB need not lie on the axis of the solenoid. So this calculation also proves that the field is uniform over the entire cross section at the center of the solenoid. Now let's discuss another application of Ampere's law, which is toroid. So here is a donut shape toroidal solenoid, or which has n turns of wire and carrying a current I, and they are very closely spaced as compared to the figure. In figure we show them far apart. So the flow of current around the toroid circumference produces a magnetic field component perpendicular to the plane of the figure. And just as for the current loop we discussed previously, if the coils are tightly wound, we can consider them as circular loops that carry current between the inner and outer radii of the toroidal solenoid. And the flow of current around toroidal circumference is then negligible, and the perpendicular component of B is negligible. So this is idealized approximation of the circular symmetry, and it tells us that magnetic lines must be circles concentric with the axis of the toroid. So we can use this symmetry and find the magnetic field. We choose circular integration path to use Ampere's law, and here in this case we choose three paths: 1, 2, and 3. So let's first consider path 1. If the toroidal solenoid produce any field at all in this region, it must be tangent to the path at all points, and the integral B dot dl will be equal to the product of B and the circumference L, which is 2 pi r of the path. But the total current enclosed by the path here is 0. So Ampere's law, if we apply the field from by using Ampere's law, the field must be 0 everywhere on this path. Similarly, if we choose path 3, then if it produce any field along path 3, the solenoid, it must also be tangent to the path at all points. Each turn of the winding passes twice through the area bounded by this path, and which has have equal currents but in opposite direction. So the net current, which is I enclosed within this area, is 0. So for this path, B also becomes 0. Now let's consider path 2, this one, this path 2. A circle with radius r. Again, by symmetry, we expect the magnetic field B to be tangent to the path, and this B dot dl here again becomes 2 pi r into dl is the circumference of the circle. Here, each turn of the winding passes once through the area bounded by path 2. So the total current enclosed by the path I enclosed would be Ni. Here N is the total number of turns in the winding. I enclosed is positive for the clockwise direction of integration. So the B is in the direction shown here like this. So here by using Ampere law, which is integral B dot dl is equal to mu naught I, we can get mu naught N I, and B is equal to mu naught N I over 2 pi r. This is your toroidal solenoid magnetic field, and the magnetic field is not uniform over a cross section of the core, because the radius r is larger at the outside and larger outside as compared to the inner side. So the radial thickness of the core is small, is as in comparison to r. The field varies only slightly across a cross section, and in that case, that considering 2 pi r is the circumferential length of the toroid, and n over 2 pi is the number of turns per unit length n, the field may be written as B is equal to mu naught Ni in a special case. So yeah, and if so it is just as at the center of a long straight solenoid, this condition shows this. So let's move to the next topic, which is about magnetic materials, and we will discuss a few type of magnetic materials today.